All right. Well, as he said, I'm Mark Ramm. I work at SourceForge. We rewrote a lot of SourceForge. In fact, at this point, most of SourceForge using various, we still use relational databases, and we now use non-relational databases. So there's a lot of tools that I've used in the last couple of years, and I just want to talk a little bit about the sort of things that you think about when trying to choose a database technology. The last few years there's been this huge bloom of non-relational databases, and people are talking about non-relational databases and NoSQL all the time. And I've used a number of tools and tried more tools than we use, and for various reasons not use them. And I think that the tools that you choose matter a lot. So this is really about choosing tools more than it is about NoSQL as a movement or something. And I learned about choosing tools before I learned about programming. And one of the things, I'm going to tell a couple of stories that I promise actually relate back. So you're going to have to trust me for like 3 or 4 minutes here. When I was a kid, I lived on an island in Florida with a bunch of hippies. And my stepdad was a carpenter, and we made a deck, and we actually screwed every board onto the deck instead of nailing them, which I thought was weird as a kid. But then a hurricane came by, and everybody's deck is gone except that one. And it takes a lot longer to screw in every board than it does to nail in every board. But it makes a difference when the hurricane comes. So that was sort of an early lesson in choosing your tools. Sometimes you choose a tool that is harder to work with because the results are going to be better. Another lesson from that same period in my life, this one a little shadier. One of our neighbors was out fishing, and he found a bale of marijuana floating in the ocean. And so he immediately grabbed it and put it in his boat and hit it with a tarp and went in concentric circles because nobody dumps just one bale of marijuana. And he found a second one, and that's all he could fit in his boat. So he went back and he tried to find it, but he couldn't find any more. But then he had 2 3-foot cubic bales of marijuana in his tool shed. Which might not, this is the moral of this story, I'm giving it at the beginning, might not be a good idea to keep the power tools and the mind-altering substances in the same shed. And so another neighbor had gone over to his shed to borrow the air hammer because he was putting up siding on his house. And he's putting up the siding, and he's like, ka-chung, ka-chung, ka-chung. And he just nails his hand right to the wall. And he's stuck to the wall, but he's fine. It is not bothering him at all. And I get home from school on the school bus, because I'm like 8 or something. And he's like, "Hey, Mark, can you bring me a claw hammer?" Okay, and I promise those stories are not just funny stories to get started. They actually relate back. See, MongoDB is a third one here. And it relates specifically to the siding story. So don't let me leave without explaining how that works. But before we get to how MongoDB, specifically how I nailed my hand to the wall with MongoDB, metaphorically, I wanted to sort of back up and talk a little bit about the part of the SQL, NoSQL divide that everybody probably knows. Who here has used a relational database? Okay, who here has used a non-relational database? Wow. So a lot of people have used NoSQL too. So I wanted to talk a little bit. Are my slides not showing? Okay, so a little bit about SQL databases. It's been sort of the gold standard for how you store your data for a couple of decades, almost 3 decades now. People use relational databases by default. Why do they use relational databases? Well, for one thing, there's 3 decades of technology and optimization behind relational databases. Postgres is amazing in many, many ways, and a lot of attention to detail and performance has gone into there. And they have tuned the crud out of all kinds of things. So it provides a really good mix of things that you need. It provides a flexible system. It's not horrible to do schema upgrades. It's pretty scalable. Like you put big hardware behind it, you can serve a lot of traffic out of a single Postgres database. And you can now replicate, like there's a pretty high degree of scalability that you can get. It's robust, you have good data integrity, you have really good backup solutions. It's simple, not in that relational algebra or relational calculus is super simple and everyone understands it completely. It's simple in that a lot of people know how to use it. Finding someone who can administer a relational database is not difficult. So it has a good mix of those 4 things. And usually you want those 4 things. So it fits. It has a DSL for a domain-specific language for querying things out of the database that everyone knows, and everyone knows how relational databases work. And it has this ACID principle. Who knows what ACID means? Okay. Another mention of the hippie island. Like I had a neighbor who every time, this is like drug reference talk, I don't know why. But anyway, I had a neighbor, all these people are neighbors, by the way, when I was a kid. I had a neighbor who took acid, not very often, but every time she did, she would freak out that she was going to have a bad trip. And so, of course, she did have a bad trip. But the only reason I bring that up is that relational databases have this atomic, consistent, isolated, and durable principle. So you know when I've made a change to the database, I always am seeing a consistent view of that database. But that's sort of true and sort of not true. When I worked for a medical records company, we moved one of our systems from Postgres to MySQL, and we discovered that MySQL has a very different point of view on this than Postgres. And everything broke, but only in 1 in 10,000 times would things not print or print twice. It was in a printing system, and it was all because we couldn't actually use select for update, which is how we were doing it before. So we were using MySQL advisory locks, which aren't even locks. They're just like, here's a string, tell me if somebody's got a lock, if they give you the same string. And it turns out MySQL is like, well, if somebody else takes the advisory lock, or if you take a different advisory lock, then that means you've given up the first one, just silently. So anyway, within relational databases, you get a big spectrum of ACID compliant to less compliant. And usually that is a trade-off between reliability and performance. MySQL without transactions and with less guarantees of durability and all of that is way, way faster than Postgres. But Postgres is way more reliable. That's become slightly less true in the last 2 years, in that Postgres has become faster and let you have the option to turn off some things that make it slower and more reliable. The other thing that relational databases have is normalization, and they have the sort of system where you can say that piece of data lives in one place and is used in one spot. But anybody who's had to make relational databases scale knows that you sort of denormalize stuff. So maybe you have somebody comes in and they're like, why is this database so not normalized? But it's for performance reasons. Or then somebody will be like, oh, well, why isn't it more denormalized? Because we need it for performance. So normalization also is kind of on a spectrum. You want data to live in one and only one place and not be replicated throughout the database in your SQL database. But when you need to scale, you usually give up some of that in order to be able to scale. So people say that they need relational databases as opposed to NoSQL for a variety of reasons. They say they can't use NoSQL, they can't use an eventually consistent system because they have money involved, or because their data is inherently relational. Like, they're like, it's tags, you have to use a relational database. There's no way to do it in a non-relational system. And I have one answer to that, which is, who wrote the paper on eventually consistent systems, and why? Okay, so Amazon, what do? They sell stuff. They use an eventually consistent data store. How do they pull it off? Like, clearly it can be done. And what you have to do, if you have an eventually consistent system and you want to do financial transactions, is that you have to actually wait until the system becomes consistent before you take people's money. So you can say, oh, I ordered this thing off Amazon, and maybe they don't have it in stock because somebody else already ordered it, but the chances of that happening are low enough that they're fine with, oh, you ordered it and he ordered it, and both of your orders go through the system, but they don't actually charge you the money until it's ready to ship. And there's enough physical time to actually get stuff ready for shipping and whatever, that the system always becomes consistent in that time. Like, even if there was a network partition and two different Amazon data stores were separate for a day, before they've shipped your item, that partition is going to be fixed. Somebody's going to fix the network downtime and be able to merge those data sets. And one person who ordered it will get the item, and the other person will get an email saying, I'm sorry, we were actually out. It will ship in 2 weeks. And that happens rarely enough, and then they give you a gift certificate or something for screwing up. But that happens rarely enough that it's worth it for them to have the super high uptime and the transaction, not database transaction, but checkout transactions that they have, to keep those things going even in the case of a network partition or a big data center fault. So why should you use a relational database? I just said that some of these previous answers were baloney. So why would you use them? I think there are good reasons to use relational database. And I'm actually going to give some more at the end. But two really good reasons is SQL. Like, SQL can be a little complicated and frustrated to use, but it is easy to use from basically any language anywhere. Like, if you have a relational database, you can query it from Python, PHP, Perl, Ruby, JavaScript, whatever. You can query it because you just write an SQL query and you get back result sets. So being able, and almost all the databases have drivers for almost every language. You're not going to get into a point where you're like, oh, I can't get at my data because it's in a relational database. Also, you get, if you can't tolerate inconsistencies for very long at all, and you don't care about latency, then relational databases make tons of sense. And for instance, when I worked at the medical records company, we used Postgres because if you say a guy got his heart medication, you really, really want him not to get it twice or 0 times. If you got a guy and he dies because your data wasn't in a consistent state and the nurse gave him the medication again and now he's dead, then you're going to feel really bad. I mean, sure, computer errors are probably kill way less patients than doctors not washing their hands, but still, it doesn't make you not feel bad when you killed a guy. Not that I ever killed a guy. No, no, we did not. It was Postgres' fault. No, I totally blame Postgres. So I could talk a lot about relational databases and what's good about them, but you all probably know that. So I'm going to switch to non-relational databases here for a second. And one thing that I sort of, over the last 2 years, have decided is that the term NoSQL is also bullshit. There's no such thing. I mean, it's NoSQL in that you don't have SQL. But otherwise, there's not a unifying theme to the NoSQL movement. There's a bunch of different things. And I think there's kind of roughly a complexity ordering here. You have key value stores like Tokyo Cabinet, where it's just a dictionary, but it's a big dictionary in the sky instead of a dictionary in memory. You have distributed key value stores, which are like Amazon SimpleDB. There's a bunch, Project Voldemort. There's a ton of open source distributed key value pairs. And these are eventually consistent. They have the idea that you could have a number of different nodes and you can talk to each node individually. And if one of those goes down, the system is still up. But otherwise, you can treat them and you get eventually consistent data. Like, eventually, it's all going to agree. But in the short term, depending on which node you talk to, you might get different results. Distributed key value stores are just one order of complexity higher than key value stores. Column-oriented stores are a whole different game. Bigtable and Cassandra do this, and they're just very much like you have. Well, again, one order of complexity above distributed key value stores in that they are distributed systems. They keep data in something like, you can think of it kind of as storing all the columns in a database together as opposed to storing the rows together on disk. And you can have complex entities within a single cell in the database. And those are very useful for a number of reasons. Then you have something that I think is actually kind of off on a totally different scale. You have things like Hadoop and MapReduce systems where they're really all about parallel processing, where you have a bunch of data, you run a map job to figure out which data you want to look at, and then you run a reduce job to do some calculations on that data. We use Hadoop at SourceForge for log analysis and figuring out how many downloads a particular project got and that sort of thing. But in some ways, it's not even really a database. It's just like there's a bunch of flat files on disk, and then there's a very simple system, or reasonably simple system, for processing those across hundreds of nodes very, very quickly. But the database part is just a file system, HDFS. Hadoop does lots of other things. It's kind of amazing and kind of scary. Then you have document-oriented stores, CouchDB, MongoDB. There's before the current JSON-based document-oriented databases, there was MarkLogic and other XML databases, but they're all document stores. There's some structured document, and you can do queries based on the contents of that document as well as its key. And that's the fundamental difference between a document-oriented store and a key value store, is that you don't just have to know the key. You can get indexed results from doing inspection of the actual document. And then you have graph-oriented stores, and graph-oriented stores can either store just key values in a very simple way, or they could be document stores where you store documents. But the thing that graph-oriented stores is that they also store information about the connections between documents. So Neo4j is a good example of this. You have a node that might be a person and has some information, like they're an employee, and you know coworkers, and it has the list of coworkers. There's a coworker relationship with this person and a coworker relationship with that person, and it keeps the connections between those objects. And then you can say, oh, who are the managers, or if you're Facebook and you want to know who are the friends within 3 of this person, you can do a query, and it will query the graph and give you back a set of objects that meet that query. If you're doing a lot of graph stuff, all the graph stuff we do at SourceForge, we actually do using Mongo. We don't use a graph-oriented store, but if you're doing lots of graph math and graph-related queries, Neo4j and people like that have optimized that. There's a huge number of NoSQL stuff, NoSQL projects out there. I grabbed a few logos, but there's dozens more, maybe hundreds now. I cannot keep up. It seems like every day someone writes a new Erlang-based key-value store. I'm like, ooh, fancy. They're like, oh, it's way better because some obscure thing that nobody cares about. So there are a lot that have sort of proven the test of time. I'm going to talk a little bit about how you would choose one, and I think before I talk about how to choose one, who knows what the CAP theorem is? All right, so I will talk about the CAP theorem. I was thinking of skipping it. The reason for the NoSQL movement is that this guy wrote a paper, and I'll show you the link to the paper. He wrote a paper in which he said, there's this theorem that I can prove that says you can have consistency, availability, or partition tolerance. Well, you can have 2 of those. You can't have all 3. It is impossible to have consistency, availability, and partition tolerance. And the basic premise of this theory is say you have 1,000 nodes in your database system, and each of them is down for 24 hours a year. If they all have to be up in order for your system to be up, and each of them has 24 hours worth of downtime a year, you have to add the downtime of your system is the downtime of all of the nodes added together. You add 24 1,000 times, you get more than 365 days. You're not up at all. If each of them is only down an hour a year, you still have 100 hour or 1,000 hours a year of downtime. That's a lot. If they're only down a minute, you still have way more downtime than is acceptable if you're Amazon.com. So if you require that all of your systems be up and connected, so the network between them works, then you're going to have more downtime. If some of them are just slaves and you can write to masters, then your downtime is really only the sum of the masters. And then you have write downtime versus read downtime. So you can mitigate this problem, but it never entirely goes away. So if you want to be 100% available all the time, if you want to have multiple data centers, if you want to have things never go down, like Amazon, who never goes down, then you need a system that allows for softer guarantees on consistency. So that I can, if, say, the database on the West Coast and the database on the East Coast, if the link between them is down, I can either block all writes because I know that I can't be consistent. Like somebody could have ordered this product here and somebody else could have ordered it here, and it's going to break. Or I can allow writes on both sides and know that there's inconsistency. And there's not really a solution that keeps everything consistent and allows for this partition tolerance. So the CAP theorem, like, because it was proven, people were like, ooh, we should fix this. And we have these problems. On the other hand, like, it's partly theoretical. Even if you use an eventually consistent system, you still have downtime, as Amazon has proven for us. And even if you use a completely consistent system and you require uptime, there's a lot you can do to get that uptime on your single relational database master up to the point where it's good enough for most cases. So my whole point about the CAP theorem is that while it's important in that it's sort of the historical reason why there is this big resurgence in thinking about non-relational databases, because you can't, I mean, fundamentally, you cannot have a relational database that is not consistent. You've given up the relational in relational databases if you give up consistency. Because ACID doesn't work at all if you give up consistency. Like, it's one of the letters, and it just doesn't work. And you can't keep part of it, and when you have a database that is inherently, everything is broken down into the smallest relations possible and normalized, then consistency becomes significantly more important than if you denormalize and handle the things in application code. There's opposite of ACID sort of principle called BASE, which is basically available, soft state, and eventually consistent. All of the distributed key value stores use this theory, this sort of BASE approach. And they use it because it's web scale. Ooh, awesomeness. I don't know what that word means, honestly. But they use this because they think, oh, we need this level of availability, we need this level of consistency, we need to be able to do all of these things, and we need incredible performance. We need more performance than we can get out of a relational database. And sometimes that's true. But mostly, I think those people have been smoking something. Because they are not going to get that much traffic. In their wildest dreams, they will get that much traffic. SourceForge, when I started, SourceForge used a single Postgres database as the store of all of its tickets and all of the data in SourceForge. We got, 45 million unique visitors a month. And, a few 100 million page views. So we had a reasonably large amount of traffic. There was a period in time when they were in the top 100 websites on the internet with one Postgres server. and it wasn't even falling over or difficult. They were just fine. Now, they weren't doing horribly complicated things. They're like showing you a ticket. But the point is, you can scale Postgres up pretty far, and we didn't even have that good of hardware. Now we have really good hardware, and it doesn't matter because it's fast enough. The point being, like, sometimes I think people have elevated ideas of what kind of scale they need to hit. And they think that they are going to have servers in multiple data centers and require uptime that they don't. So they get pulled into distributed key value stores and that part of NoSQL because it's web scale. Like, I'm doing an internet startup. I have to have these things. Otherwise, it will all fail. No. Turns out lots of internet startups use relational databases, and it works out fine. And there's also big, fancy stories of when Big and Reddit and whoever switched from a relational database to Cassandra or some other non-relational database and had many, many difficulties. Not, I think, because Cassandra is a bad tool or anything, but for the reason that I mentioned earlier in the story that I promised I would get back to, which is if you don't know your tools and you don't know what you're doing, or you're just foggy mentally, you can make mistakes. And since you can't necessarily control, well, the point being, like, they didn't know their tools. When we started using Mongo, we didn't know it. I'm going to come back to this slide. But when we started using Mongo, we didn't know our tool very well. We were using Mongo to serve just the project summary, download, and file browse pages on SourceForge. That was our first little test case on SourceForge itself. We replaced those 3 pages. We improved the user flow. We cleaned them up so that instead of taking 5 clicks to get your download, like if you went to the project summary page, there was a big green button that knew what browser you were on and therefore what operating system you had and gave you the right link. Ooh, fancy. And we used Mongo for that project. And Mongo was way overkill in terms of serving the traffic we needed. And yet when we put it in production, when we tested on my laptop, I could serve all of the traffic for SourceForge off my Mac laptop. I was like, hey, that's pretty good. But then we put it in production, and it was a little slow. And we hadn't tested with a quite complete real data set. And we were storing all of the releases of a project in its project record. Well, some things, like JBoss, for instance, have a lot of releases because they have a lot of little components, and they have 10 years of releases for all of those little components. So they have thousands of releases. So the project record for that was almost 4 megs. Actually, it was just over 4 megs because that's the limit in Mongo, and it wasn't working for a while. But we got it down under 4 megs, and it worked. But we were pulling that out of the database and taking it to the web server every request. So we were pulling a lot of data. And our Mongo server was slow. We didn't know why, and I've given it away now. Why? But Mongo was super fast on my laptop, slower in production. We looked at CPU load. It was like none. We looked at disk I/O, none. We're like, what is going on? Why is this server slow? Because we had a gigabit network card connecting the two, and it was completely saturated. We were shoving a gigabit of data at the server continuously. So we, as a very short-term fix, we bonded the 2 gigabit network cards on there, put them on the same subnet so we could get 2 gigabits of traffic between. And this is all to serve, I don't know. We grab 4 megs of project data and serve a 30K HTML page. So we were a little crazy, and we were doing this, and but we didn't think, oh, my database server could be overloading my gigabit network. Because in relational database world, that is never going to happen. Like, if you can get Postgres to overload a gigabit network, you have really, really fast server. And we did not have that server. We had some junk commodity crap. So that's sort of the story of how I nailed my hand to the wall with MongoDB. By not knowing that, or sort of only just beginning to know the capabilities that it had. It was very, very powerful. Like, it can serve a gigabit of traffic out of the database, no problem. Like, it doesn't even flinch. Like, no CPU load, no disk I/O, it was just fine. Now, that was a relatively small data size, and it mostly fit in memory. Your mileage may differ. But we didn't know the limitations, and so we didn't even know where to look right away when we saw some performance issues. When we did figure out where to look, it all worked, and things got better. Okay, so to go back to the taxonomy, my point about CAP and my point about the MongoDB, what appeared to be a sidetrack story, is that your tools matter. Knowing what tools you have matters. Knowing how they work matter. And the reason to choose a non-relational database, in most cases, is not because of some abstract theoretical thing about the CAP theorem and scalability. The reason to choose a non-relational database is because it works better for what you need to do. If all you need is to store some values by key, and you know you're never going to have to query them, and those values are just abstract entities, and you couldn't query them anyway, like you couldn't query within them anyway, a key value store is perfect. It's going to be faster than any of the other options that are available. Like, you're not going to get a database that is faster than Tokyo Cabinet for storing key values. Although, yeah, don't have too much data. And then maybe if you have a lot of data, you might want to find a different key value store than Tokyo Cabinet. Because write performance can get bad at the far edge. A distributed key value store, that is a case, you choose a distributed key value store because you need to scale beyond a certain level. And you need availability beyond what you could get without that sort of soft state CAP theorem stuff. Column-oriented stores, there's reasons to use those. There's not, Cassandra is really the only open source alternative, and you have to write your own indexes. There's work if you go down the Cassandra road. MapReduce systems, like say you have a ton of log data and you just want to query out of it. Having Hadoop to do that and having a large number of servers so that you can actually query your log data quickly by some measure of quickly. Quickly compared to what you could do on a single node. Not quickly like you could from a relational database. But if you have terabytes and terabytes of data, MapReduce systems make all kinds of sense because you can actually run ad hoc queries across all of that data and use the computing power of a large number of machines. Document-oriented stores, I'm going to talk a little bit extra about those because that's what I've been using a lot, and what sort of MongoDB and CouchDB sort of fit in a sweet spot in the non-relational database system for me, in that it's what I get back is very close to a Python dictionary. And it's very simple to take a data structure that I'm used to using in Python and store it in this system and then get it back. And that makes programming easier because I don't now have to think, oh, well, I have this project that is, there's a project, and inside the project there's a list of releases, and then there's also a list of contributors, and there's also a description. You know, I have a data structure that is a project record. Instead of saying, oh, well, how do I turn that into a bunch of tables and figure it out? I just store that thing. into Mongo, and then I can get it back, and I can query by things. So I can say, I need all the projects where in the list of committers is Joe Schmo. And Mongo will go out and look at all of them and get them back. So it has a query language. It has the ability to look inside documents and understand document structure. That means that I can get more done faster. And really, that was what it was all about. We have these structures like this that are project records. We wanted to be able to query them. The query language in Mongo is very much, you pass it a dictionary that is the query parameter. So you say x:3 and y:foo, and that's the equivalent of select star from document where x equals 3 and y equals foo. Mongo also has things where you can do partial updates. You can update just one field in a document, and document updates are atomic. So when you update a document, you know that that document either got updated or did not. But partial updates let you just update one field in a document very, very quickly, and it has operators like increment. So I can keep a download count just by incrementing the download field in a counter. You can set just one field, you can unset, you can push to a list, you can pop. So you can use Mongo for storing all kinds of data and doing operations on that data in a simple way. You can do conditional updates in Mongo. I don't want to talk too much about Mongo just because it's the one we use at SourceForge, but it does, the reason we chose it is that we did performance testing of a bunch of solutions. Its performance was way above what we needed. So we knew it was going to work. We did the availability calculation, and Mongo did not have and does not have an eventually consistent soft state. That basically, the base system, it is not that. There is a server of record. Writes, if you can't write to any master, writes block. You can have multi-master and failover, but at a certain point, you can get to a point where you have enough servers down that you're not going to be able to write. So it is not like Project Voldemort or Dynamo or any of those distributed key value stores that gives you the you can write no matter what guarantee. But the uptime was going to be way higher than we needed if we configured it right. The performance was way higher than we needed, and it was very, very easy for us to use. So that is why we chose it. The programming task, we had a short time, we got it done. The performance was good. It was very successful. We got to do more stuff. My sort of conclusion here is that you need to figure out what your app needs and what you need to do. Just saying, I want to use non-relational database doesn't necessarily work. And I have plenty of other stories I can tell you. You also need to not obsess about scale that you never need. We were really worried. I was very worried about scale when we did the consume, the project summary, download page, and files page launch of the new SourceForge in Python, because I was afraid, because the first thing we were doing at SourceForge in Python, and there was a lot of concern in the company that it wasn't going to scale. And so I worried obsessively about making sure that it scaled. But MongoDB, we could do 18,000 writes a second on a Mac Mini that I was using for testing. So not server scale hardware. And we could do 8,000, tens of thousands of reads per second, and that was way higher than our traffic rate. We do not get tens of thousands of downloads per second. So, we get hundreds. So Mongo was going to be fast enough. And Postgres would have been fast enough, but the reason we chose Mongo was because we needed the tool for the job and the performance. So we looked, is this tool what we want to use? And then we said, does it work? Will it scale to the level we need? So we figured out what we needed, and we were storing projects. We were not storing complex sets of data that were related in complex ways. There was just a project, and everything tied back to the project. So it was very easy to figure out how to map that to a document system. We've since used Mongo for a bunch of other reasons. We've used Hadoop. Before I used CouchDB for another site. I tried to do a bunch of things in Cassandra, and then we gave up, which is not to say that other people should give up, but Cassandra really is, if you need a level of performance and a level of scalability above what SourceForge or Reddit or Dig or those sorts of people need, if you are Google or Amazon or you're ginormous, you should be considering things that are one level up from Mongo in terms of scalability and performance. But I don't think that's necessary for everyone. And certainly hasn't been necessary for us, and I think 99%, well, way more than 99% of people will be well served by the scale that you can get out of the system, whatever system fits your problem best, as opposed to focusing on scale first. And then, if you're scale too far, you can always change. At that point, you have lots of users. You probably have money. It's easier to fix it later than it is to fix it first when you don't have money. So, question?
One question?
Yeah, and I went too long.
I don't have a lot of experience with NoSQL databases, but it's my impression that it's easier maybe to convert and iterate and rewrite declarative code, the declarative schema and the queries to procedural ones. I mean, if I start with Postgres because it's good enough, I try and keep my code simpler because it lets me do many things that I wouldn't do in MySQL, for instance. And with a simpler code, it would be easier to convert parts and bits to NoSQL when I need to. Or should I really think hard at the start?
That is a good question. So the question is, is it easy to convert from one to another, and should you think hard at the start? And certainly I think it is not that difficult to convert from a relational database to something like MongoDB. We did it at SourceForge for the project record stuff. And that project, we had 6 weeks total. Dealing with Mongo was maybe one of those weeks. And we were like 4-person team. So it wasn't a lot of work went into the Mongo part. Most of the work went into getting the UI right and figuring out how to display the right big green button and that sort of stuff. The other way can be harder. So I don't think it's, on the other hand, if you're trying to move to Cassandra, that is a bigger step. So if you feel like you need really to go the eventually consistent and have the soft state, that is going to require huge changes in your application, because now your application has to understand when it's okay to have database inconsistency and when it's not, and you don't have transactions in the database, you have transactions in your code. So that change is huge.
Yeah, just a question about, I was interested that you put simple DB in the distributed key value store category. I'd always seen it more as a document store. So I wonder what the distinction, for example, the query interface is very similar.
Yeah, so it's probably, I should not have put it there. Like that was, I put it in distributed key value because it has soft state and eventual consistency and that stuff, which I was categorizing in that. But it does have the document query system. So it really belongs in both categories.
Don't you think that every data is somehow related? For example, for your project pages, aren't they related to users and something like that? How do you request all the projects which belong to a user, for example, in relational?
So there's two things that you do. What we do is we have a list of admins for a project in the project. So we query Mongo and we say where user is in admin. Give us back all the projects. But then on the user, we have a list of all their projects. So that data is actually stored in two separate places, not in one place. And that's how we keep. So you can keep data related. You're just not using the database's integrity checking in the database to make that happen. You have to write code to update both those places when you change a user's connection to a project. And that is one of the things you have to do if you go to a document-oriented store. And there's a big disadvantage to that in terms of now you're managing something in your code that the database used to manage for you. And whenever somebody else can write code to manage difficult problems for you, that is a good thing.
I have actually two questions. So
Okay.
the first one is a continuation, relate, not to relate. What do you, from your own experience, to embed or not to embed?
To embed the database or not to embed?
Embed a document inside of the document or not to embed.
Oh. I don't embed, mostly. We haven't had any bad experience with it. We tried it and then we stopped because it wasn't really getting us anything over just doing a second query to get the other document.
Okay. We still have many questions, but we are out of time.
I'll be outside.
Mark will be outside, so thank you.